Welcome to the deep dive. Today, we're taking a journey, a really big one, using Carl Sagan's Cosmos as our map. We've gathered some incredible pieces from it, science, history, philosophy, all rolled into one.
It's such a landmark work, isn't it?
It,
Connecting the
it,
dots from ancient watchers to, well, us.
exactly. Okay, let's unpack this, our mission today, to explore how we humans have looked up at the universe, how our understanding has shifted from, old myths to modern science, and crucially, what does looking out there tell us about ourselves right now?
And what's fascinating here, I think, is that it's not just about the facts piling up. It's about these turning points, these moments where we actually changed our minds about really fundamental stuff.
Often against a lot of pushback, right?
Oh, absolutely. Huge resistance. It's really this ongoing tug of war between, let's say, observation and reason versus superstition and dogma. Getting a handle on that struggle helps us see our own spot in the cosmos a bit more clearly.
That's a great way to put it. And you don't have to look too far back for examples of challenging those beliefs. I mean, take Eratosthenes. We're talking around 200 BC.
Incredible story.
Right. He basically nails the size of the Earth. And how? With sticks and shadows. Simple as that.
Seems simple now, maybe.
Yeah.
But the thinking behind it.
He saw that at noon, on the solstice, a stick in Syene cast no shadow, but hundreds of miles away in Alexandria, it did. What does that tell you?
It tells you the ground isn't flat.
Mm-hmm.
If the sun's rays are coming in parallel, which they pretty much are from that distance, the only explanation for the different shadows is curvature.
Exactly, that aha moment. The Earth must be curved. And he didn't just stop there, he calculated the circumference.
And got remarkably close.
Huh?
It just shows what you can achieve with careful observation and, maybe more importantly, trusting that observation over what everyone else just assumes. It shows the universe kind of talks back if you listen.
Imagine figuring out the size of our whole planet just by looking at shadows. It really shows what human curiosity can do, even with, well, pretty basic tools back then.
But, like you said, that trust in evidence often ran into trouble.
And Eratosthenes wasn't the only one thinking big, even earlier. You had the Ionians, people like Anaximander, Democritus.
Yeah, Anaximander, what, 600 BC? Talking about humans evolving from other creatures, infinite worlds out there.
Seriously ahead of their time. And Democritus, 5th century BC, he gives us the word atom, unable to be cut.
From that thought experiment, right? Trying to slice a cone. He figured if you keep cutting, you must eventually hit something fundamental, something indivisible. Atoms.
Just incredible foresight. Almost sounds modern.
It does. But that brilliance didn't guarantee smooth sailing for science. It's strange, isn't it? You have minds like the Pythagoreans giving us foundational math.
The Pythagorean theorem, yeah. The idea of cosmos itself, a harmonious universe ordered by number.
Exactly. But then they found things that didn't fit their perfect harmony, like the square root of 2.
The ratio of a square's diagonal to its side couldn't be expressed as a nice, neat fraction.
Right. An irrational number. And for them, whose whole system was built on the beauty of whole number ratios, this was, well, deeply disturbing.
Like finding a crack in the foundation of reality.
Pretty much. So what do? They suppressed it, said it was dangerous knowledge. Same with the dodecahedron, that 12-sided shape. Too dangerous to talk about.
It raises that question, doesn't it? Why would these brilliant thinkers, people seeking truth, actively fear and hide certain discoveries?
It really highlights that tension. Seeking truth versus protecting a worldview that feels safe and comfortable. And there was another factor too, wasn't there? Something about how society was changing.
Yeah, those early Ionians, they seemed to connect theory and practice. They weren't afraid to get their hands dirty, to experiment.
But then slave economies became more dominant.
Exactly. And suddenly, manual labor, which includes doing experiments, gets looked down on. It becomes undignified for the thinkers.
So the people with the time to think stopped doing the practical work.
Pretty much. And when you separate thinking from doing, from observing and testing, well, science tends to stall.
Which it seems to have done for quite a while.
Yeah, despite those early flashes, fast forward 1,000 years, and we're largely still thinking the Earth is the center of everything. Which brings us to Claudius Ptolemy.
Right, 2nd century AD. A major figure. He did a lot for astronomy, cataloging stars, predicting eclipses, understanding the Earth was spherical.
But he also locked in that geocentric model, Earth, at the center. And maybe just as significantly, he systematized Babylonian astrology, gave it real intellectual weight.
And that model, supported by the church later on, basically put the brakes on astronomy for, 1,400 years? It's amazing how powerful an incorrect idea can be when it gets institutional backing.
And think about how deep that astrological thinking went. You mentioned the words.
Oh, right. Disaster. Literally bad star in Greek. Or consider with the planets. Our language is like a fossil record of these old beliefs. People really thought the stars ruled their lives. Bad star. Huh. Changes how you hear the word. So it took until Copernicus, 1543, to formally propose the sun-centered model.
And even then, his book was published as he was dying, and the church eventually suppressed it. The fight wasn't over.
Not by a long shot. Which leads us to Johannes Kepler, born 1571. He's such a key player in this shift.
Kepler's fascinating because you see the struggles so clearly in him. He starts off very much in that Pythagorean mindset, his first big idea, the cosmic mystery.
Trying to fit the planet's orbits into nested platonic solids, right? Those perfect geometric shapes.
Exactly. He wanted the universe to be built on that kind of perfect geometry. It was beautiful. It felt right.
But then he got access to Tycho Brahe's data.
And Brahe was meticulous. Probably the best observational data gathered up to that point. Just raw numbers, positions of planets, night after night.
And here's where it gets really interesting, I think, the human part. Kepler tried to make the data fit his beautiful theory. He really tried.
For years, but it wouldn't quite work. Especially Mars. It was always a little bit off.
And eventually he had to face it. The data was right, and his beautiful idea was wrong. He famously said he preferred the hard truth to his dearest illusions. He realized the planets weren't moving in perfect circles.
They were moving in ellipses.
Ellipses. A less perfect shape, maybe, but
Right.
That's what the evidence showed. It's such a powerful moment in science, letting the facts lead you, even when it means giving up something you love.
It says so much about what real science is about, doesn't it? Not confirming biases, but being willing to be wrong.
Absolutely. And Kepler's struggles weren't just intellectual. He was living in a time when superstition was still incredibly powerful.
Right, that story about his mother.
Yeah, she was accused of witchcraft. Old, eccentric woman, herbal remedies. It was enough. Kepler had to rush back, use his training in logic and evidence to defend her, to save her.
So his personal life mirrored that larger battle. Reason against fear, evidence against superstition.
It really did. And that same battle played out with comets. For centuries, they were nothing but bad news.
Harbingers of disaster, right? Celestial beards, flowing hair, crucifixes in the sky.
Terrifying signs. Ptolemy thought they brought war and hot weather. They just didn't fit the neat, orderly clockwork heavens everyone imagined. They were unpredictable intruders.
Until Newton and Halley basically changed the game.
Newton's laws of motion and gravity showed that comets weren't random. They followed orbits, just like planets, mostly very elongated elliptical orbits.
And Halley took that idea and ran with it. He looked at records of past comets.
Notice the sightings in 1531, 1607, 1682 seem similar. He crunched the numbers using Newton's math and predicted it would come back.
In 1758.
And bang, there it was. Halley's Comet. Suddenly, these terrifying apparitions were predictable, part of the natural order, a huge win for reason.
But the cosmos still throws curveballs, like Tunguska, 1908.
Oh, yeah. That massive explosion over Siberia, flattened trees over an area the size of a major city, likely a piece of a comet, Comet Encke probably, exploding in the atmosphere.
The eyewitness accounts are wild. Heat like your shirt's on fire, people blown off their feet, the ground shaking.
And the initial reaction from the government. Basically, it's too remote, not worth investigating. It took over a decade for anyone to get out there.
A very different response than we'd see today, hopefully. It's a reminder, isn't it? The cosmos isn't just out there to look at. It affects us directly.
Definitely. It actively shapes our world, our history, even our fears.
Which sort of loops back to the biggest question, life itself. Where did it come from? Sagan had that beautiful phrase that life's origin and evolution, given enough time, is a cosmic inevitability.
Because the building blocks are everywhere. Organic molecules aren't just an Earth thing. They're abundant in interstellar clouds and meteorites. Earth was like a fertile ground, a molecular garden of Eden.
So you start with simple stuff in the oceans.
Hydrogen-rich molecules, yeah. Add energy lightning, UV light from the young sun, and they start linking up, forming more complex molecules, amino acids, nucleotide bases.
Pieces of proteins and DNA.
Exactly. And then, maybe purely by chance, one molecule forms that can make rough copies of itself. The dawn of heredity.
The ancestor of DNA.
Right. These replicators get better, maybe get enclosed in membranes, forming the first cells. Then comes photosynthesis, changing the whole atmosphere to oxygen-rich. Then multicellular life, and then sex.
Ah, the invention of sex, a game changer for evolution.
Huge. Instead of just copying errors, you're mixing and matching whole sets of genetic instructions. It massively speeds up evolution, leads to that incredible diversification, the Cambrian explosion.
And all this leads eventually to us, and specifically to the human brain, which is itself this amazing product of evolution.
It really is, and you can almost see the layers of that history inside our heads.
How so?
Well, deep down, you've got the brain stem, the oldest part, running basic life support, breathing, heartbeat, stuff fish have.
Okay.
Then wrapped around that is the R complex, the reptilian complex, aggression, ritual, territoriality, social hierarchies. Sagan called it the crocodile brain within us. Still there.
Yeah.
Then the limbic system, the mammalian brain, more complex emotions, parental care, mood, memory.
And finally, the big one.
The cerebral cortex.
Yeah.
Especially developed in primates, massively so in humans. This is where the magic happens. Thought, analysis, language, foresight, self-awareness, matter contemplating itself.
So it's like an archaeological dig in our own skulls. All those older parts are still active?
Oh, yeah. They're running ancient programs. The cortex tries to manage them, rationalize them. But the tension between reason and our deeper, older drives is always there. It's fascinating. The brain holds something like 10 to the 14 bits of information.
That's what, 20 million books worth?
Roughly. Far, far more information than is in our genes. It's this incredibly complex, evolved machine.
Which, of course, makes you ask, if it happened here, could it happen elsewhere? Are we alone? The Drake equation tries to get a handle on that.
Right, trying to estimate how many civilizations might be out there. Lots of factors. Star formation rates, planets, life arising, intelligence, technology.
But Sagan argued the real unknown, the big question mark, wasn't the astrophysics or the biology.
No. It was L, the lifetime of a technological civilization. Do societies like ours make it through their technological adolescence without destroying themselves? That's the kicker.
That hits close to home. We've even started looking, haven't we? Viking on Mars?
Trying to find microbes. They had experiments like the wolf trap, put some Martian soil in a nutrient broth and see if anything grows and breathes.
Did they find anything conclusive?
Ambiguous results, unfortunately. But it raised another tricky issue. Back contamination.
Meaning?
What if we bring Martian samples back and they contain microbes that could harm Earth's biosphere, or even us? We worry about aliens invading, but maybe the danger is microscopic and we bring it on ourselves.
That's a sobering thought. It flips the script.
It does. And thinking about contact, history gives us some complicated lessons. Sagan brought up La Perouse's encounter with the Tlingit in Alaska, late 1700s.
Relatively peaceful, right? Though based on misunderstanding.
Yeah, the Tlingit, who had no concept of sailing ships, saw them as great blackbirds with white wings, the sailors as small black messengers. But their oral tradition, though filtered through their culture, kept a remarkably accurate core account for generations.
Okay, so contact doesn't have to be disastrous, but then you have Cortez and the Aztecs.
A completely different story. The Aztecs had this incredibly sophisticated civilization, astronomy, calendars, cities, writing. But Cortez arrives with guns, steel armor, horses,
And disease.
and disease. Total technological mismatch. The Aztec accounts describe the cannons just shattering mountains, the sheer terror and destruction. It was swift, brutal annihilation of whole civilization.
So what's the takeaway for potential extraterrestrial contact?
Well, Sagan argued that any civilization capable of interstellar travel would likely be vastly more advanced than us. If they wanted to harm us, they could. But maybe, he hoped, advanced civilizations overcome those aggressive tendencies that Cortez embodied. And a radio signal, unlike a conquistador's ship, is as light as a kiss. It's information, not invasion. Our fears might just be us projecting our own history.
That perspective, seeing ourselves in that larger context, is powerful. It's what Sagan called the cosmic perspective, looking back at Earth from space.
Suddenly borders vanish. Nationalisms look petty. All those fanatical, ethnic, or religious chauvinisms, as he put it, seem absurd against the backdrop of the cosmos.
But here's the terrible irony. The very tools that give us that perspective, rockets, radio telescopes, nuclear power sources for deep space probes,
Are the same technologies used for weapons of mass destruction, especially nuclear weapons.
it's the ultimate paradox of our time. We reach for the stars while holding the ability to extinguish ourselves completely.
The sheer scale of the nuclear arsenals built up during the Cold War. It's almost incomprehensible. Tens of thousands of weapons. Sagan calculated the total destructive power was like fighting World War II every second for an entire afternoon.
And beyond the immediate horror, the long-term effects.
A full exchange could ignite massive firestorms, pumping soot into the atmosphere, blocking sunlight nuclear winter. It could also burn nitrogen high up, destroying the ozone layer. Years of lethal UV radiation bathing the planet.
Killing crops, plankton, triggering total ecological collapse, maybe irreversible.
So it raises that profound question. If we, who are, as Sagan said, the latest manufacturers of the galactic hydrogen industry, the universe made conscious, if we don't speak for Earth, who will?
Is there a way out of this trap?
Sagan believed there was. He saw the choice as stark: the universe or nothing. He argued that embracing space exploration, this grand project dedicated to life and knowledge, not death, could be transformative. It could channel those same technological skills, the same military-industrial capacity towards a common peaceful goal, foster a sense of global unity, that pale blue dot consciousness. Plus, its actually economically smart study showed exploration yields significant returns on investment.
So survival here and reaching out there are linked.
Inextricably. Our future depends on managing this planet and looking beyond it.
Okay, so we've journeyed from ancient Greeks squinting at shadows to the potential search for life on other worlds and the stark choices facing us right here. It's been quite the deep dive. It really hammers home that continuous human quest for understanding, for finding our place, and that connection. We really are made of stardust.
We absolutely are. And, the point we're at right now, historically, it feels as critical, as much of a turning point as when those first Ionian scientists started questioning the old myths 2,500 years ago.
How do you mean?
Will we let that ancient, deep-seated evolutionary baggage, the aggression, the tribalism, the fear win out and keep us trapped here, maybe leading to our own demise? Or will we listen to what Sagan called our great soaring passionate intelligence? That same curiosity that drove Eratosthenes and Kepler, will that lead us to embrace the cosmos and maybe a more unified future for ourselves?
It really puts the choice in sharp relief.
It does. And that choice, it's ours to make. Right here, right now, on this small, fragile world. Just, a tiny flash in the immense darkness of space and time.